Hi guys! Today we are going to start our discussion in chapter 23. We are going to start off with knowing how to find the electric field from using Coulomb's law. And what that means is we are going to be looking at some different geometries and how we can use calculus to find the electric field, not from a point charge, because that's just a simple equation, but from a different combination or arrangement of charges. And then we're not going to get into Gauss's law too much on this video. I'm just going to kind of talk to you guys about like the intro to Gauss's law, because that will be a little bit of a longer video later. So we can use calculus to help us find the electric field due to a variety of geometries. Today in this video we're just going to talk about specifically two kinds, like a rod, a long rod or string of charges, and then we're going to look at a hoop or a ring of charges. And this is very different. It's very different than just looking at one singular point charge or even 2 or 3 point charges arranged in space, because now we have a whole bunch of charges that are put together along a much longer distance or a much greater range. So we can use calculus to help us do this. If we look at the electric field as being an integral, it's the integral of our Coulomb's constant times the dq, or how the charge changes over a particular distance. And we can sum these up using integration, right? So we have to integrate over the entire length of the charged object, whether that is a rod or a ring or whatever. So before we do that, though, we need to have a little discussion about what charge density means and how to define that. So depending on the shape that we're looking at, right now we're going to be looking at, I think, just one-dimensional things at the moment. We have a couple of different ways that we can describe the charge that is sitting on the object. So the first is essentially if you're looking at a 1D object, like a wire, something that's long and thin and narrow. So if you have a long, thin, narrow, supposed to be kind of straight there, and it's totally carrying a charge, we're going to say Q. The linear charge density, we define that as being a lambda, is going to be Q over L, right, or dQ over dL. If we're looking at the entire length, then L we typically say is capital L, and Q is the total charge. So the linear charge density is Q over L for the entire length of the wire or the rod. So this is just telling us approximately, as your length changes along the wire, how much charge is on that particular chunk or on that particular length. So if I'm just looking at a tiny piece of the wire, let's say here, linear charge density would help me to figure out how much charge is just on this little tiny length, or this dl. It's changing my length. If the surface is 2 or 3 dimensional, and it's the charge is distributed around its surface, so we typically have this when we talk about spheres. And in a lot of our problems we're going to have like conducting spheres, hollow conducting spheres. And in those cases all of the charges, right, sit on the outside. So we have to talk about how this charge is distributed on the area of the conductor. And this is a good way to do that. So this is lowercase sigma, and it means surface charge density, and that is dq over dA. So again, depending on what surface area we are looking at, how much charge is present on that particular chunk of surface area. If we're looking at the whole entire sphere, well, then it's the whole entire charge over the whole entire area. And then the last thing we can discuss is volume. So sometimes we have a solid insulator or a solid conductor or something like that, and the volume, not a solid conductor, sorry, solid insulator, and the charge is distributed throughout the entire object itself. And so now it's not just a question of surface area, the charge is sitting on the outside of it, but it is a question of how much charge is occupying the entire volume of the sphere. So in this case we have volume charge density, which is rho, lowercase p. That's dq over dv. Again, if we're looking at the entire volume, then we are looking at the entire charge that's present spread. Okay, so the first example we're going to do is looking at an electric field due to a line of charges. You can think of this as being like a rod of charges. So here is our x-axis, right? And we're going to sit this line of charge here on the x-axis. And we are going to distribute a charge throughout this line or this wire. And what we're going to do is we're going to look at a point way out here at the edge. We're going to call that point P. And we want to find the electric field at this point due to this string of charges. Now, we can't just treat this like a point charge because it extends across a length, right? It extends from 0, or the origin, out here to what they're calling L. So we're going to try to keep stuff a little bit straight in our head, and we're going to say that this location out here, this point P, we're going to call that x naught, just for the purposes of integrating everything. So if we're going to choose some super tiny portion of this string of charges, which is what we kind of have to do whenever we're integrating, we're going to take a super tiny portion and then subsequently add up all of those tiny portions together to get your value. We can say that this tiny portion is at some spot along the x-axis that we're going to call x. And the distance from here to here is x naught minus x, of course. So this is what we're going to use to define our distance from our portion here, our small chunk of line charges, to where we're trying to find our electric field. So our geometry is a line, so we're going to use our lambda, or our linear charge density, to help us talk about what's happening with our electric field. So I have a little thing that says to go to the whiteboard, so that means I need more room. So let's take a look here. So we know linear charge density. My computer is lagging. We know that our linear charge density is lambda is equal to dq over dl. Okay, so we know that our lambda is equal to dq over dl, and consequently dq is equal to L times lambda. Oops. Okay. So our integral for our electric field, this is going to be important because our integral for our electric field is this formula, right? But we're going to substitute this in for our dq. Let's do lambda first, just to make it a little cleaner. Lambda dl. Lambda dl over, and this is not going to be r squared. Remember, we when we drew our initial picture, we had rod of charges and we had some point out here, and we're looking at a small integral section here. And we labeled this at point x and this at x naught. So we're going to call this x naught minus x squared. Alright, so just to make sure that everything is in the same terms here, instead of saying lambda dl, I'm just going to change that to be lambda dx because I'm integrating, or this rod extends along the x-axis, so the length of it will change along the x-axis. So I'm just going to change that to be x instead of L. All right. So if you guys are handy on calculus, you can go ahead and try to integrate that, but I'm going to do it for those of you guys that might not know. So K is Coulomb's constant, L is going to be a constant for this particular length. So those two values can just come out of our integral, and we've got dx over x naught minus x squared. Okay, so essentially what I have here is 1 over x naught minus x squared times dx. I like to write it like this. Just helps my brain a little bit. Okay, so we're going to use the substitution method here to integrate this. I'm not sure if you guys are at this point in your calculus yet, but I can see that there's a function down here at the bottom on my denominator. So I'm going to say that x naught minus x is going to equal u. And then when I take du with respect to dx, I get negative 1, right? So that means that negative dx is equal to du. So I'm going to use this idea here and here, and I'm going to plug this into my integral. So what I'm going to get is negative 1 over u times du, right? And that negative came from the fact that dx is negative du, essentially. All right, so I can integrate. The negative can come out. So I can integrate 1 over u because that is, 1 over u squared. Oops. So I can integrate 1 over u squared if I use my power rule, because 1 over u squared is u to the negative 2. So I'm going to add 1 to that power, and I'm going to divide by the new power, which gets me u to the negative 1 over negative 1. U to the negative 1 is 1 over u. So this is going to be negative 1 over u. But then I have this floating negative out here to the side. So my integral is really, my answer is 1 over u. But I defined u up here as being x naught minus x. So my answer is x naught minus x. So how does that fit into our original integral? Well, we had k lambda. We had that pulled out. And then we had our integral, which is 1 over x naught minus x. And we're going to evaluate this. If I didn't write this up here, I do apologize. We're going to evaluate this from 0 to L, right? Because if we look back at our PowerPoint, we can see, or in the picture that we drew, the length of the line of charges extends from 0 to L. So that's how far we are going to evaluate our integral, those charges along that line. So this goes 0 to L. So we do that. We have k lambda, and then we're going to have our answer for the first part, which is 1 x naught minus L minus 1 over x naught. Yeah, I guess it could be a curly one. Okay, so now we can just find a common denominator here between these two fractions. And you end up, so that you can actually like add them together. I can't do those little parentheses. You end up getting L x naught minus L. And then we can put our k lambda back in. to that expression. And we get this for our electric field, which is fine and dandy and makes sense, but we know we can simplify it a little bit more because we know that lambda, if we're looking at the entire length of the line of charges, is Q over L. And so lambda times L has to be Q. So we can say KQ over X naught minus L times X naught. And this becomes our electric field, or our expression for our electric field. So the question that is going to arise here from all of this is, what happens if you think about it, if X naught is much larger, so X naught much larger than L. Well, at that point, essentially your L becomes nothing, or 0, and you end up with KQ over X naught squared, which is our typical formula for electric field. So essentially what this is saying is that regardless of your geometry or your setup, if you go super far away from the object, you can treat that object, whatever it is, like a point charge. So let's go into a second example here. And now we're going to look at a ring of charges. So this picture has a lot going on in it. Pause it if you need to and just kind of absorb what's happening here. But this was the best graphic I could find online for this because I really did not want to draw this scenario. So we have a ring of charges now where that is centered at the origin, and the normal to this ring kind of points along the x-axis. So what they're asking for is the electric field at a point along the x-axis. They call this point P. And so here is your ring, and they say this ring has a charge of Q on it. And so they're saying we're going to look at this little tiny sliver of distance along this ring that they're going to call ds in the picture. And that little chunk, right, contributes a charge amount that they're calling dq. Now, due to this little tiny piece of this ring here, it does contribute to the electric field at this point, just like this little chunk contributes and this little chunk and etc. But the cool thing about this geometry is that if we assumed that this was a positive charge, which it is in this case, the electric field due to this little orange piece, since this has a positive charge, would point away from it, right? But it would point away from every single chunk of charge that's in this ring. So this one would point this way. This guy's electric field at this point would point up. This guy's electric field would point maybe this way, right? So what you're going to get, this one here would point up this way. So what you're going to get here is a situation where you have a high amount of symmetry. If you look at what you have going on with each of these vectors, each vertical component is canceled out by another vertical component because you're going in a circle, right? So all of the verticals, this guy has a vertical component down. Well, this guy has an equal and opposite vertical component up. So all of your verticals will cancel out, and the only thing you really need to worry about is what's going on in the x direction, because all of these x direction vectors from the electric field will add together to make one electric field going along the x-axis. All right, so let's go back. I'm not. All right, so let's just write this in on this page. Since all you're looking for, and in this case they wrote this little alpha, but I like to do it as an omega symbol. So all you care about, if this is your vector right here, your electric field vector, this red one, pinkish one, all you care about is this horizontal component, because that's the only one that's going to contribute. So we can say dEx equals kdq over r squared times, this is just your electric field, right, cosine theta. Now in this case, what is cosine theta equal to? Well, cosine theta is adjacent over hypotenuse, which in this case our adjacent vector, or our adjacent distance, is x in this geometry. And then our hypotenuse is going to be r. They're calling it r in this graphic. This hypotenuse, this distance from here to here. So that's r. Now, your r is square root of x squared plus a squared. So when I put those two things together, I get k dq. Now r squared is just x squared plus a squared times x over just regular r, which is square root x squared plus a squared. Now, when we put those two things together, we get k. My pen died, I think. Oh, wait, no. K dq. Oh, it died. Oh, no. I'll have to handwrite it. K dq x over, now this is like to the power of 1, right? And this is to the power of 1/2. So add those together, you get 3/2 x squared plus a squared to the power of 3/2. Okay, and all of that equals dex. But we need to integrate that, right? So integral of d of both sides is ex, because the integral of dex is just ex. And then in this case, every one of these terms is going to be a constant. Because the k is just Coulomb's constant. The x value is not going to change because the x value is the distance along the horizontal axis, the x-axis, and it's going to be the same for every point along this circle. So that part's a constant. And a is a constant as well, so everything comes out of the integral except for dq, and the integral of dq is just q. So your answer ends up being kq over x squared plus a squared to the 3/2. Sorry, that looks so bad, guys. My pen died in the middle of this, which is what you see kind of down here. Okay, so two little follow-up questions. What would the field on the axis of a ring charge be when x equals 0? Well, when x equals 0, you are right here in the center. You have no horizontal components. All you have are vertical components contributing to the electric field, and they all cancel each other out. So the electric field at 0 will be 0. And then what happens when x is much, 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 much larger than a? Well, you guys hopefully know that from the last example, is that it will essentially become a point charge, and it will just be kq. Kq over x squared. And if you look at the geometry, that's what happens. Or, I'm sorry, if you look at the algebra, that's what happens. Okay, so we're going to start talking about Gauss's law, and in order to talk about Gauss's law, we need to talk about flux. So let's talk about what flux means. And flux is flow. Essentially, it's how much of something is flowing through a particular area. And in this class, we're going to denote flux as this phi symbol. And so flux equals the electric field that is passing through a particular area. You can think of it like flow, electric field flow. Here's a little graphic to show you if this is my area, this square sheet here. My flux would be the strength of the electric field that's traveling times the area that is traveling through. So if the area that we're concerned about is not exactly perpendicular to the field, then we have to take into account some angles. So if now instead of being perfectly perpendicular, straight up and down, it's tilted slightly, well, that's going to reduce our flow or our flux. The only component of the electric field that contributes to the flux is the component that is traveling perpendicular to the surface. So if this is my field, these pink lines, and this is my surface, if I draw like a normal vector, like a vector perpendicular to the surface of the square, then what I'm looking for is going to be the, draw this line up here to complete the triangle. What I'm looking for is this angle here, the cosine, right? Because I want the cosine component of this vector so that I get the perpendicular component. You know, not so much right now. So here's just a little example for you guys. You guys can read it. The answer is already posted there for you. But electric field of a particular strength passes through a rectangular area that has certain dimensions. The field makes an angle of 30 degrees with the normal. Determine the electric flux through the rectangle. So we're going to use EA cosine theta. Our electric field is E, 2100, and our A is 22 times 28, and then our angle is going to be 30 degrees. So that one's just a plug and chug once you calculate what the area is in meters, of course. Okay, so let's talk about a closed surface. So if we have a point charge sitting out here in space, and we're going to look at our region away from the point charge. So this yellow blob is just some randomly closed surface we've drawn away from the positive charge. So it's important that you guys understand that flux is always perpendicular to the surface. So the same flux that's coming in on this side will come out on the other side. And so because of that, the net flux through a closed surface is 0. If this positive charge was like inside of this surface, well, that's a different ballgame. We're going to talk about that later. But if the charge is sitting outside of the closed surface, the flux through any closed surface is 0.